Now the next topic in this series is the total emissive power and Stephen Boltzmann law. Out of the various laws for the thermal radiation, Stephen Boltzmann law is very important. As per this law, the energy radiated by a body, which is in the form of emissive power, is directly proportional to the fourth power of its absolute temperature. The meaning is the emissive power is directly proportional to the fourth power of absolute temperature of that body. Now the total emissive power, which is E, total emissive power of a black body, which is EB, may be obtained by integrating the Planck's distribution equation over the entire wavelength. The wavelength range starts from 0 to infinity. If we take the integration of the EB lambda with respect to d lambda, we get the answer, which is the total emissive power of the black body, and the final result will be EB, which is the total emissive power of black body, will be equal to sigma Td4, where T is the temperature of the body and sigma is the Stephen Boltzmann constant. We know the equation for monochromatic emissive power of black body. We already know the equation, which is given by Planck's law. That value of EB lambda, we will put the value of EB lambda in this equation, which is in the form of constant C1, constant C2, lambda and temperature T. Then we will do the integration and solve this equation. After simplification, we will get the result for total emissive power of black body. Final equation will be in the form where you will find EB is equal to T raised to power 4 multiplied by a constant value, which is 5.67 into 10 raised to power minus 8. This value 5.67 into 10 raised to power minus 8 is the value of Stephen Boltzmann constant, and its units are watt per meter square Kelvin raised to power 4. Next, there is a topic which is gray body and its emissive power. Gray body, if a surface of a solid body absorb a definite percentage of radiation, irrespective of wavelength, then that body is known as gray body. The absorptivity, which is represented by symbol alpha, is equal to, or it varies from 0 to 1. It varies from 0 to 1. If the alpha varies with wavelength, that type of body is called the colored body. There is a variation or a plot in between monochromatic emissive power and wavelength. On this graph, the representation of variation of E lambda with respect to lambda for black body, for real body and for gray body is presented. For the case of black body, we can easily understand for the black body the value of peak, the value of total emissive power is maximum, and the value for a real emissive power is irregular, and there is an approximation which is known as gray body approximation, which will be represented by a smooth curve, and this is for gray body. If you want to find the emissivity of a gray body, it will be a ratio of emissivity of a gray body to the emissivity of a black body at a particular temperature T. Emissive power of a gray body will always be less than emissive power of a black body at a given temperature. One important point about the emissivity and absorptivity is that emissivity, which is represented by symbol epsilon, of a surface is a property of the surface. It depends upon the characteristics of the surface and it is independent of wavelength. When we will compare the emissivity with the absorptivity, we will say absorptivity, which is represented by alpha, is not a property of the surface. It depends upon wavelength. This is the difference between emissivity and absorptivity. As per the Kirchhoff's law, alpha is equal to emissivity and it is valid only. As per the Kirchhoff's law, alpha will be equal to epsilon emissivity, and it is valid only if the wavelength of incident radiation and wavelength of emitting radiations are same. Next is Kirchhoff's law of radiation. It states that the ratio of emissive power of a body to its absorptivity is always constant. To understand this, let us consider three bodies: body 1, body 2 and body 3. Their emissive powers are, let's say, E1, E2 and E3, and their absorptivities are alpha 1, alpha 2 and alpha 3. As per this law, the ratio of these two quantities, emissive power and absorptivity, is constant. It means E1 divided by alpha 1 will be equal to E2 divided by alpha 2 and so on. There is another statement in the form of emissivity and absorptivity. That statement clearly says that the emissivity of a body is equal to the absorptivity when the body remains in thermal equilibrium with its surrounding. Means if these all bodies are in thermal equilibrium with the surrounding, then we can say that epsilon is equal to alpha. Next is the Wien's displacement law. The monochromatic emissive power of a black body for different temperatures are represented with the help of a plot which is in between emissive power of the black body and wavelength lambda. As per the Planck's law of radiation, which is given by the equation EB lambda is equal to C1 raised to power lambda raised to power minus 5 divided by this quantity. When there is a change of wavelength lambda from 0 to infinity, the monochromatic emissive power of the black body changes. First it is 0, then it increases, it reaches to its maximum value, then it decreases for a particular temperature T. Now, as per the Wien's displacement law, according to the Wien's displacement law, which relates temperature and wavelength, which is lambda m, for the maximum value, this is a relation which we can say the product of lambda m and absolute temperature is always equal to constant, and its value is 2.9 mm Kelvin. If we are interested to find the value which is maximum value EB lambda, we have to differentiate the value EB lambda and put that value is equal to 0. We know EB lambda is equal to this. We will put the value here and we will differentiate it with respect to lambda. After simplification, we will get the relation in the form of lambda m and T, which is the temperature, and it will be equal to 2900 micron Kelvin. Next is solid angle and intensity of radiation. What is solid angle and what is intensity of radiation? To understand this, we are going to consider a hemisphere. It is a hemisphere whose surface area, total surface area is A2, and its radius is capital R. We have placed a small area dA1 at the center of the hemisphere, and this area dA1 is radiating energy in all possible directions. We are going to consider another area, small area at the surface of the sphere, which is dA2. To understand more clearly, there is a 3D diagram for this. In the three-dimensional diagram for the hemisphere, the small area which is placed at the center is dA1. It is represented by this shaded area. and the total area is A2. It is the total surface area of the hemisphere. The area which is on the surface of the hemisphere was small area was dA2, and it is also represented by this shaded lines. We are interested to find out the amount of energy received by this area dA2. And similarly, by integrating, we will be interested to find the total area received by the total surface A2. Now the amount of energy received by area A2 means the total area A2 from small area dA1 can be calculated by introducing a new concept, new term, which is known as solid angle. Now what is solid angle? As per the definition, solid angle is defined as the angle covered by the unit area on the surface of sphere of unit radius when joined with the center of the sphere, and it is measured in steradian. Mathematically, solid angle is represented by omega, which is equal to A upon R square. A is the total area and R is the radius of the sphere. Now, the intensity of radiation. The second term is the intensity of radiation. Intensity of radiation is defined as the rate of emission of radiation in a given direction. Per surface, per unit solid angle, per unit projected area of radiating surface on the plane perpendicular to the direction of radiation. What does it mean? It means it is the energy radiated by a body per unit area, per unit time, per unit, we can say, the solid angle. Now we know that dA1 is located at the center of the sphere. We know that dA1 is located at the center of the sphere. The hemisphere of radius capital R, the amount of radiation falling on this dA2. First of all, we will calculate the amount of radiation falling on this dA2 on the surface of the sphere. Let's say it is dE. It can be calculated by the definition of intensity of radiation. Means it is equal to intensity of radiation of area dA1. Intensity of radiation of area dA1. The symbol for intensity of radiation is IB1 multiplied by the projected area. Projected area of dA1 cos of angle phi, and multiplied by solid angle. So we can say that where IB1 is the intensity of radiation of the black body, which is placed at the center, and the area is small dA1. Now the solid angle made by the area dA2. What will be the solid angle made by area dA2? It will be, we can say, solid angle made by area dA2. It will be dA2 divided by radius the square. When we will use these concepts, when we will use the definition of solid angle and intensity of radiation, we will be able to find the relation in between EB and IB. We will be able to find the relation between emissive power of black body and intensity of radiation of the black body. After simplification, after putting the value, after simplification, the final result will be EB will be equal to pi IB.